Okay, here we go with some free response questions. Write the standard formation reaction for CH3OH liquid, aka methanol, from methanol's constituent elements. So the enthalpy of formation, or the standard enthalpy of formation, is always the elements in their standard states and then an arrow leading to the compound and 1 mole of that in its standard state. So we can write the right-hand side of CH3OH, standard state liquid. Excuse me, and by standard state we mean 25 degrees Celsius, 1 atmosphere of pressure, and 1 mole of the substance. So remember, you always need 1 mole of it right here as the product. So to write this in its standard state, we need carbon in its standard state. Carbon is a solid at 25 degrees Celsius. Plus hydrogen. Hydrogen, of course, is diatomic and it's gaseous at 25 degrees Celsius. We need to have 4 of those total, so I'd have to put a 2 here. And then we need oxygen. And oxygen, of course, is also diatomic and it's gaseous in its standard state. To make it so we'd only have 1 oxygen over here, we'd have to put a 1/2 in front of it on this side of the reaction to make sure that it's balanced. But there is the equation for the standard enthalpy of formation of CH3OH. Question number 2 is not tested this year. Question number 3, name the following, or given the following standard enthalpies of formation, and it gives a list right here, calculate the enthalpy change for the reaction. So standard enthalpies of formation are given in your textbook, and you also have Appendix C that gives you many more of them. And then there are there's an equation that allows you to find the enthalpy of the reaction using the enthalpies of formation. And so the equation is always enthalpy of reaction is equal to the summation of the enthalpy of formation of the products minus the summation of the enthalpy of formation of the reactants. And so in this particular one, we would take the products right here, and reading them off from the chart right here, NH3 would be negative 46.2, and there's only one of those, plus HCl, which is negative 92.3. That's our products. And then minus the reactant NH4Cl, which is negative 315.0. And then we'd subtract those. Remember, minus and minus becomes a plus, and we end up with 176.7, and then put kilojoules on there in the end. All right, also try this one. This one has some enthalpies of formation right here, and then we have products minus reactants here. So our products are HCN, which would be 135.1 positive, and then we'd add that and multiply that by 2 because there's a 2 right there, and then we'd have H2O, which is negative 285.8, and you'd have to multiply that one by 6 because there's a 6 in front of there. That'd be our products minus our reactants, and the, let's see, the reactants then would be 3O2, and notice O2 is not given on this list, and the reason that oxygen's not given on this list is because anything in its elemental state is 0, so it'd be 3 times 0 for oxygen. And then there's 2 NH3s up here, so 2 times the NH3, which is negative 45.9. And then there's 2 of the CH4s right here, so 2 times the CH4 is negative 74.9. So products minus reactants, don't forget anything in its standard state that's in its elemental form is 0. And so then when you add those together, subtract those guys, add it together, it ends up being negative 1203 kilojoules. Question 4. The specific heat capacity of lead is, how much heat is required to raise the temperature of 10 grams of lead from 20 to 40 degrees Celsius? So the equation here is Q is equal to M times C times delta T, where C stands for specific heat capacity, M stands for mass, triangle T stands for temperature change, which is temperature final minus temperature initial, and Q, of course, is heat at constant pressure, and so we can replace delta H with it, sometimes with a little P below it, sometimes a little P below it, meaning that it's at constant pressure. So let's put our values in. So we're looking for Q, and that would equal the mass, which is 10 grams, times the specific heat capacity, which is 0.128 joules per gram degrees Celsius, or Kelvin, because remember the space between a Kelvin and 1 and 2 Kelvin is the same as between 1 and 2 Celsius, so you can use those interchangeably when you're looking at a change. And then our temperature goes from 20 to 40, so 40 minus 20, or 20 is our change in temperature. And then we multiply those together, and we should end up with 25.6 joules of energy is required. Letter B. A 250 gram sample of lead with a specific heat capacity, once again here, has an initial temperature of, what is the final temperature when 2.75 kilojoules are added to the sample of lead? So now we're looking for the final temperature, and so when we write this equation, Q equals M times C times delta T, temperature final minus temperature initial, the thing we're looking for is the temperature final. You can also just go ahead and solve for delta T right here, and then know that you can plug it into this equation once you find delta T, because delta T is equal to that. So first thing you have to do is take your kilojoules of heat and make sure that they're in joules, because notice that our specific heat capacity is in joules. So kilojoules to joules is 3 to the right, so 2750 joules is equal to the mass. And the mass is a 250 gram sample of the lead. And then the specific heat capacity is 0.129 joules per gram degrees Celsius. And then we'll just put delta T right here, and we'll look for delta T. And our change in temperature let's do it on the calculator right now so you can watch me do it, and you can check my work as well, would be 2750 divided by 250, 250, enter, and then divided by 0.129, enter. So 85.27 is our change in temperature. So delta T is equal to 85.27, and that's equal to temperature final minus our temperature initial, which was 22. And so then we have to solve this little algebra problem by adding 22 to both sides of the equation. And we find that the final temperature is equal to 107.3 Celsius.